So we'll continue on dust and dependence on inclination from Redshift 1.5.
Okay, can people hear me? No. Like this. Okay. Yeah, so good morning, everybody. So I will continue on this topic on dust. So it's about dust attenuation law and the galaxy inclination at the intermediate redshifts. So I will also discuss how can this tell us about the information about the distribution of these dust grains inside the galaxies. I will not say that this talk is done with my advisor, Susan Carson, and also many other collaborators, including Sandy here and Greg here. Why do we study dust distribution? I would say that there are so many great progress being done in recent days to incorporate this dust into the models of galaxy formation. But there are some difficulties that prevent us from going further to understand the dust in full details. I have two thoughts here. First, we know dust is both in the diffuse interstellar medium and also H2 regions. So this H2 region can be really small, like 10 parsec, which is below the resolution limit of the typical simulation of galaxies. So probably we still do not have a very good handle of such small system, the star-forming regions, as people talked about this before. And also, they have huge influence if you want to match the simulation to the observation, because everything has to be obscured by dust, so the ICDs of these galaxies can really change. Because I have 30 minutes, please allow me just to start with conclusions. So I use this so-called ARX beta relation to study dust attenuation. I find for massive star-forming galaxies, this relation is dependent on galaxy inclination. This is just consistent with a two-component model of dust distribution. Young stars are in shells, and the older stars, they are just mixed up with the dust. I also want to state that such relation from observation can be a benchmark for the spatial dust distribution in the future galaxy simulations if they can reach finer details of the dust. The data of observation is from the CANDELS survey. I have 129 star-forming galaxies, about 10 to the 10 solar mass. This is what we call massive star-forming galaxies. And the infrared from the Spectra 24 micron. Also, I have the U-band from the ground-based and the HSD bands to measure UV spectral shape. What is ARX beta? So ARX is just simply the luminosity ratio between air and the UV. Dust absorbs the UV light and emits the mid to far infrared light. So this can be a nice indicator of the line of sight dust attenuation. UV spectral slope beta is what you can get if you want to fit a power law to the UV spectrum. Just remember that low value of beta means galaxy looks blue in the ultraviolet, and the large value means galaxy looks red. Here I put two very simple distributions of star and dust in the galaxies. This tells you how can different distributions influence the so-called ARX beta relation. Horizontal one is the UV spectral slope. Vertical is the ARX in log scale. For this shell model, you would say galaxies go to the upper right if I increase the dust content of this system. But for the mixture model, you would say the vertical value can increase a lot, but the UV spectrum, it doesn't change very much. This is because in such kind of system, the UV light is dominated by the stars that is close to the system surface, so these stars have lower reddening compared to the other stars in the system. Now I go to the observations. What do the real galaxies look like in the LX spate diagram? Individual points, they are individual galaxies. And the large dots, they are medium trends. Here I find a very interesting trend that the adjunct galaxies stay above the face-on galaxies on this diagram. We would think that if you change your viewing angle of the same kind of galaxies, the stellar population shall not change, but the relatively alignment between stars and the dust, they can change along your view line of sight. Now I overplot the observation, the median trends as dots, with the radial transfer models as the dashed curves here. We could immediately tell the face-on disks, they look like the shell model, and the adjunct disks, they go up a little bit, and maybe there are more distribution from the adjunct disk, the mixture model. This is indeed the case. If I made the so-called hybrid model, it's just a combination between the shell and the mixture component. So the red solid curve, they have a higher attenuation from the mixture component. Now the tau V is the so-called effective attenuation. So it's not what Sandy says, the one that is larger than the AV. This is just proportional to the attenuation in the V band. And the shell plus mixture, this one in blue color, they have much lower attenuation from the mixture model. I think this kind of argument can be summarized with this really simple cartoon here. So this is a disk galaxy, and the very young stars, they are blue symbols. They are surrounded by these spherical shells. Maybe you would say this is an oversimplification, but this is just what I can do for now. And the attenuation from the shells, they do not change very much as the viewing angle changes. However, the attenuation from the mixture component, they can just vary a lot if you change your viewing angle, because the sight line through the disk increases from the face-on case to the adjunct case. Okay, here I go back to the conclusions. I use this so-called LX spate iteration to understand the spatial distribution of dust. And we found this can be explained by a two-component dust model. Young stars are surrounded by local shells in their H2 regions, and the older stars, they are mixed with dust. Finally, I want to say again that this relation may be useful for future simulations if they can get a better treatment in really small scales and also large scales. And maybe something like sunrise skirt, they can improve based on this and check the spatial dust distribution from very recent simulations. Yeah, here's all. And finally, I want to say the background photo. This is the Milky Way, probably the most well-known adjunct galaxies. Yeah, I just want to remind you, incarnation really matters. Okay, that's everything. I will stop and take questions.
Any questions on dust? Yep.
Yeah, that also. Yeah, so I'm not sure. I'm not sure I got this geometric argument. So could you explain a bit why there's more contribution from the diffuse component? If you look edge on, would you look the edge on?
Go to adjunct, please.
Yeah. So. Yeah, so this part, I mean, is very interesting, but I'm not sure. Yeah, could you say a few words about that? Geometry? Yeah.
Oh, yeah. All right. So the mixture model. By mixture model, I mean the stars that is have like reddish color or kind of bluish color in the diffuse dust. So the shades here, these are the diffuse interstellar medium, and they are just mixed with the stars all the place. And in the adjunct case, you see through the disk in a very long distance, and this dust column in the diffuse interstellar medium is high.
More questions?
Stanley has emphasized the importance of size. I was wondering whether you had a chance to separate your galaxies by, let's say, roughly large galaxies versus small galaxies, and whether they differ qualitatively in either the dispersions and or the mean values.
Yeah, that's a very good point. So now I only have 100 galaxies, so the statistics is still small. Yeah, I think in the future, I can combine like all the 5 CANDELS fields and go to wider redshift range. Yeah, and also with size, you can have early type galaxies, compact galaxies, they can mix up with the disk sample. Yeah, I'm not sure how hard is that to figure out.
Sandy?
I wonder if it would be also good just to look at somehow appropriately normalized infrared flux rather than IRX, which is divided by the ultraviolet flux. It would be nice to have a parameter that we think doesn't depend on inclination a priori.
Yeah, that's a nice point. Actually, we have the figure in the paper. It really shows that the infrared luminosity, they do not change with your inclination because the emission is isotropic. And UV light, the adjunct galaxies have lower luminosity compared to the silicon galaxy.
One last comment.
As you mentioned, the codes that try to include some of these effects, the sunrise code, which does have this basic pattern of local attenuation around star-forming regions, and then screen for the larger distribution of dust, and the Rayonon's approach. Those do predict an IRX beta relation that is somewhat similar to what you're finding in the actual galaxies. Have you actually made a comparison with the Sunrise or the Narayanan code to see how well they do in detail?
Yeah, thanks for the comment. Yeah, as I know, Sunrise, they incorporate analytical models to treat the shell dust, but yeah, I haven't checked into the inclination dependence. Maybe I can do it for further stuff, yes.
So we have images from our simulation, and they represent all different inclinations. So you're welcome to have access to those. You can use those effects.
Yeah, thanks a lot. We can talk later.
Okay, so let's thank the speaker again.